Thanks, Avi. So the story is that we started working on this problem in summer 2013 when I was an intern with Nikhil at Microsoft Research India. So we made very little progress on the problem. So whatever progress we made, I showed it to Avi. Somehow Avi felt bad about us working on this problem, and he said, okay, let's work on non-commutative permanents and determinants. So mission accomplished.
Anyway, it was a good idea.
Yeah, so anyways, so 3 years later, so I saw this crazy generalization of the Golden-Thomson inequality in QIP, which seemed to be the missing link. But yeah, I mean, the inequality looked crazy. I thought it won't work, so I didn't try it. It's bad. But a couple of months later, Nikhil saw the same inequality on the blackboard of his colleague. So he said, let's try. This might fix the proof. So we tried. It actually worked. But yeah, we were off by some log epsilon factors. And later, Yintat and Zhao, they went into the black box of this Golden-Thomson inequality. They made the bound optimal. So then we decided to merge the papers. Okay. But yeah, so yeah, it's a nice inequality, but we don't have any applications. It would be nice to find applications. Okay. So I'll tell you what this inequality. Okay. So let's start with so what is the vanilla Chernoff bound? So it says that you have x1 to xk, which are independent real valued random variables, and they are bounded. Let's say they're bounded by absolute value 1 and their mean 0. Okay. Then the probability that the sum gets too large, sum over I xi greater than epsilon, is at most 2 times exponential minus k epsilon square over 4. Okay. So yeah, so you have independent real valued random variables. Their sum is concentrated around 0. Okay. So so this is something we have all seen. So there are 2 extensions. So one is for dependent random variables, and the other one is for matrix valued random variables. So we'll see both of these 2 extensions, and what we'll do is sort of combine these 2 extensions into one. Okay. So any questions? Okay.
Not that it's important so much, but the constant 1 over 4 is optimal in this setting?
Think it might be optimal. Do people know? I mean, it might be optimal.
It's not optimal.
It's not.
Oh,
it's 2. Okay.
Yeah.
Okay, it doesn't matter. So yeah, our constants will be horrible. So yeah, it doesn't matter. But you're right. Maybe in this setting you can write the optimal constant there. Okay. So yeah. So what is this setting of dependent random variables? So there are various things you can consider. The thing that's relevant for this talk is taking a random walk and an expander. Okay. So let me first briefly tell you about expanders. So in this talk we'll just deal with regular undirected graphs. So G will be a regular undirected graph. Okay. Let P be the transition matrix of this graph G, or the random walk matrix. Okay. And I'll denote lambda of G. So let the eigenvalues of this matrix P be lambda 1 to lambda n. These are the eigenvalues for P, and I'll denote lambda of G by so lambda 1 is equal to 1 and lambda g will be the maximum absolute value of the eigenvalue which is not 1. Okay, so maximum over I not equal to 1, absolute value of lambda I. Okay, so lambda g. Okay, and I'll call. So I'll say the graph is a lambda expander if this quantity lambda of g is at most lambda. So the operational meaning is that the transition matrix shrinks any vector in L2 norm by lambda if it is orthogonal to the all ones matrix, or in other words sum over I xi equals 0. Okay, so any vector orthogonal to all ones vector, the transition matrix by shrink by lambda. Okay.
Are you okay with bipartite?
Yeah, because
No,
that's our plan.
no, yeah. Okay, with bipartite.
absolutely
Yeah. Yeah. So what is the expander Chernoff bound? So it basically says that if you take a random walk on an expander, even though you're not getting independent random variables, you sort of get you get the same Chernoff bound. Okay, so let me say, so we'll have a function. So you label the vertices by real numbers, and again they'll satisfy the same properties, the bounded, mean 0 and so on. So f of v is at most 1 and sum over v f v is 0. Okay, so it's bounded and mean 0. Then so this is not. So when you take a stationary random walk on the graph v1 to vk, so this means that you start with a uniformly random vertex and then you take a random walk. Then the probability that the sum of the values that you encounter, this is at least epsilon, is at most again 2 exponential, again we won't worry about the constants, k epsilon square divided by 1 minus lambda, which is the spectral gap. Okay, so this is the bound. So you take a random walk and you sum of the values you encounter. These are also concentrated around 0 if the graph is an expander. Okay.
Probably want to put some names next to this.
Oh, sorry. Yes. Sorry. Yeah, this is. Yeah, so they have been studied in various forms before also, but I guess this particular bound was proved by Gilman in '94.
The others are not really.
The strongest one is Gilman in '94. Okay. Yeah, so basically if the graph is, let's say, a 0.9 expander, up to constants you get the same bound as you would get if they are independent random variables. Okay. So any questions so far? Yeah, so
Does this kind of a theorem extend to vertex expanders other than just eigenvalue expansion?
I haven't seen
There is a
such a thing.
connection between the. I mean, if you have
For
a
constant
expansion, then you have special idea also. So.
For constant degree graphs,
Yeah.
that is a
This
reason.
for any degree. It doesn't depend on the degree. In particular, it's also for constant degree.
This is
That's the amazing thing. That holds for despite the huge correlation between the x's.
Yeah, so there are two things I want to mention. Two comment. So
I think this implies factorial. So, because if you look at the second moment, it implies something in the second moment. So this cannot be true for
So it cannot be
expansion,
factorial.
just because it's not the same notion. It's equivalent to factorial.
Okay, so two comments. So first of all, qualitatively, this is what you should expect, because you can look the following example. If the graph is disconnected, right? So you can have two components of the graph, and let's say the size of these components is the same. Then and your function f, you can take the indicator function for the set A. Then when you take a random walk, what does this random variable behave like, right? So this random variable, either initially you start in this component, then you'll stay here, or you start in this component and you'll stay here. So this random variable will be 1 with probability half and 0 with probability half, right?
Well, maybe
So
you want -1 on the other side, so it's the average is 0. So
oh, right, okay, yes, right, good point, yeah. So maybe, yeah,
-1.
right. So there's no concentration where the graph is disconnected, and yeah, then you can design examples where, yeah, sort of quantitatively what you get is also there. Okay. Okay. Yeah. So qualitatively, this is what's going on, and so yeah. So quantitatively, it's much easier to get bounds where this decay sort of this loss depends on the mixing time of the graph instead of the spectral gap. Okay. So if you wanted exponential of minus k square over something like t mixing time square, this is much easier. Basically, yeah, you start with v1, then you look at the walk at time t mix and so on. So this walk is roughly independent, like sort of v1 is roughly independent of t mixing, right? So you can decompose the walk into sort of various nearly independent walks, but this is the loss you'll get, okay? But t mix is usually something like log n over 1 minus lambda, okay? And usually this log factor is too much to pay for applications. Okay? So yeah, so typically, so the k that you are interested in is either constant, so we'll see an application, or typically log n or something like that, okay? And then yeah, there's no, you can't sort of decompose into nearly independent things. So yeah, so the magic is that sort of, yeah, there's dependence just depending on the spectral gap. And it's an expander, yeah, it's up to constants the same. Okay. Questions? Okay, yeah, so I just want to quickly mention example application. So we have this. There's something written here. So yeah, I mean, so yeah, so example application. So I mean, of course, we'll be in reducing the amount of randomness. So so reducing randomness in error amplification. So suppose you have a
Can you write a bit
bigger.
for the,
Hold on. Okay. Okay, I'll try. So let's say you have a randomized algorithm A for computing some function. Let's say on n bits. Okay. And the two properties, the error of this algorithm is 1/3, and it uses s random bits. Okay. So then, if you want to reduce the error to 2 to the minus k, you can of course do it by repeating k independent times. So you will get some bound, so you'll use s times k random bits in the, so this can do, okay? So you can repeat k independent times and just take majority of something. But in fact, using this expander Chernoff bound, you can do using just s plus order k random bits. Okay, so this is using Chernoff bound. and this is using expander Chernoff bound.
And you need to know that there are explicit expanders that you can describe on exponentially sized graph.
Yes, that's right. Yeah. So I won't go into details, but yeah, you will build a graph, expand a graph on 2 to the s vertices. You can't explicitly write it down, and but yeah, they are strongly explicit constructions where sort of you can describe the neighbors in polynomial time, and then you will take a random walk on that expander, and do the same thing.
Exactly what
So sorry, error means that so for you fix an input, what is the probability over the randomness of the algorithm that you output the correct value? So that is 2/3, at least 2/3, and that the rest is the error.
Is there anything hiding in the omega? Like, is there dependence on f or on the?
No.
On
So this omega is just an explicit constant. Yeah, I don't remember what's the current best thing, but let's say 80 or 1 over 80 or something we have that should do. Okay, questions? Okay, so this is the dependent random variable setting, and then I'll tell you the setting of matrix valued random variables. Okay, so it's called the matrix Chernoff bound. And yeah, so this was first proven by Halswert, and Winter in 2002, and then Trop later generalized this in many directions. Okay, so here, yeah, we are in a similar setting, just that these matrices are these random variables are matrix valued. So you have x1 to xk, these are independent random variables, and again mean 0, and the spectral norm is always upper bounded by 1.
Is right equals 0.
Sorry. And they are, so yeah, so they are matrix valued. In fact, they are d by d Hermitian matrices. Okay, that's this support set. Then probability that the spectral norm of this average is too large is at most 2 times exponential minus k epsilon square over 4. So right now it looks exactly like the Chernoff bound, but there's a factor of the dimension 2d. Okay. Yeah, so you have mean 0 random variables, matrix valued, then the average is, the spectral norm is large, is at most this bound, and the same up to a factor of dimension. Okay, and this factor of dimension you have to pay. It's easy to see. Basically, if you think about diagonal matrices, then it's like sort of d independent instances of the usual Chernoff bound. Okay, so you have to get this using some union bound kind of thing. Okay, any questions? Yeah.
What's the difference between the two papers you cited? The second one.
So yeah, so this version was proven here, but yeah, Trop has many sort of extensions and also improvements in the bounds and so on. Not in this setting, but in some other settings. Okay. Okay, if this is clear, then yeah. So now we are ready to state our main theorem.
And this paper uses the usual golden Thomson.
Yes. So yeah. So the proof of this uses the golden Thomson inequality. Yeah, so the main theorem that we prove so like again let G be a lambda expander, and we'll label now the vertices by D by D Hermitian matrices. Let me denote it by HD. See, so these are D by D Hermitian matrices. Sorry if this notation is not standard. And again, you have the same things. It's mean 0, that sum over V FV is 0, and also they're bounded. Norm of each FV is at most 1. Okay, so this is the same setting as there. And then you take V1 to Vk is a stationary random walk. Okay. Then the probability that the sum that you encounter along this random walk, the spectral norm of that gets too large, is at most, so it bound will look the same, exponential minus omega k epsilon square over the spectral. Okay. So it's exactly the analog of the usual scalar expander Chernoff. Okay. So this is the main theorem. So you label the vertices by matrices, then you take a random walk, sum of the matrices, and that sum is concentrated around 0. Okay. So any questions? Yeah, so let's see. Okay, I was going to do this application. Yeah, I guess maybe let me mention this application just so that you can see that maybe this theorem could be useful someday. Okay. Yes.
Is there a multiplication
Where?
1 minus lambda? Yeah.
This?
As lambda is close to 1, it should worsen.
Yeah, so the 1 minus lambda is in the denominator. Sorry. Okay, you're right. Sorry. Or maybe in the previous one also it stated incorrectly. Yes. Yeah, sorry. Yeah, the previous one also, sorry. Maybe this already deleted. Yeah. Okay, so I'll mention this application, which is from the, yeah, so I should say that this was, yeah, as Avi said, yeah, this was conjectured in the paper with David Shao. Yeah, so again an application. So this is again from Avi's paper with David, and yeah, so I'll call this constructing expanders from expanders. Yeah, so the subject is this theorem by Allen and Reutemann from 93, and the proof we'll see is due to Landau and Russell from 2004, and also Lowe and Schulman. Yeah, so funnily Nikhil saw this Golden-Thomson inequality on the blackboard of Landau. It's interesting. So so the subject is that, let's say you have an H which is an abelian group. Oh, this is true for any group. Yeah, that's true. But it's optimal for abelian. So yeah, so H is a group on n elements, and then So might have seen the Cayley graph of H. So S is some subset of H which is closed under inverses. Okay. So yeah, for technical reasons we'll allow S to be a multiset. Okay. And then closed under inverses means that there should be equal number of occurrences of S and S inverse. Okay. Then the Cayley graph of H with respect to S is so this is what the vertices are in H, and H is connected to H prime if there exists S such that S in the set multiset S such that HS equals H prime. Okay. So if some element in this set S can send H to H prime, then we'll connect those things. And since it's closed under inverses, it's an undirected graph. And since S is a multiset, we'll also allow multi-edges in case there are multiple elements. Okay, so this is a Cayley graph. And so the theorem due to Allen and Roykman is that so you take log n over gamma square elements S1 to let's say k sk, and you also take their inverses to make it closed, and you'll call this S. Okay.
It's random.
This is random, yes. So take these many random elements from the group, and then write the Cayley graph, and this will be a gamma expander. Okay, so that's the theorem.
With high probability.
Sorry, with high probability. Yeah, so take roughly log n random elements from the group, construct the Cayley graph, will be a gamma expander with high probability. Okay, that's the theorem. And then in the paper with David, so Avi and David, they gave a deterministic polynomial time algorithm to construct S. So given the multiplication table of H, you can in deterministic polynomial time construct this S. Okay, so that's what they did. And yeah, okay, so I'm running out of time. I won't describe you how, but basically the proof of Landau and Russell and others, so they proved this using the matrix Chernoff bound. You can construct basically the permutation matrices corresponding to the group elements, add them up and so on. And so initially they planned to use the expander Chernoff bound to de-randomize this. So that wasn't there, but they used some other methods. But yeah, now you can just do this by running instead of picking these randomly, you pick them up using an expander. Okay, so you do a random walk on an expander, pick these group elements, construct the Cayley graph. There will be an expander with high probability, and then you can this be log n amount of randomness. Then you can brute force over it to construct it deterministically. Sorry if it was fast. Yes.
So you said that this is better for abelian groups?
No,
this
the
hardest.
Oh.
Yeah, I mean you might even need log n elements to generate the group. So, and I mean even to say that it's connected, you'll need log n things, and yeah, for abelian. But yeah.
For concrete groups like Z must be, you can take powers of 2, right? That would be an expander, or
It's not so.
powers of 2 is going to be the characters are Lacanary, so I guess
It's not, this is generalized for, it's not that.
so what happens for powers of 2? That's the moment.
You propose something.
But it is an expander.
What is this? Yeah, to propose the logarithmic number suffices requires what?
No, specifically for the powers of 2 as a generator. I think
Two may not be a generator anyway, but
the power. No.
yeah.
It's fully generated.
Yeah, it's
Then you can expand it.
I think so, but it's not so. Just the fact that it's not always a generator tells us something.
You're right.
Okay. Yeah. So yeah, I won't go into more detail. You can ask me offline what the details are. But yeah, you can use the expander Chernoff bound in particular to de-randomize it, recovering the theorem of Avi and David. Okay. So now let's go into the proof. So yeah. So I'll just sort of. Yeah, I mean, just to see sort of where this Golden, Thomson and things show up, let's first see what you do for the usual Chernoff bound. So it's, I guess we have all seen gazillion times. So you have this thing, then you want to reduce it to sort of computing the moment generating function. So you'll take exponentials, introduce a parameter t. This is equal to the same as the probability that sum is getting equal to this is the same as the exponential is getting equal to e to the t k epsilon. Here t is some parameter greater than 0 which will pick later, and then you use Markov to do this. Okay, and then yeah, so there are two steps here. Okay, both trivial in this case but non-trivial in the generalizations. So now e to the sum is the same as product over the exponentials. So this is same as product over I e to the t xi over e t k epsilon. So here we used that it's scalar case, right? So e to the a plus b is e to the a times e to the b, and then it's also you can take the so since these are independent, you can take expectation inside. So it's product over I expectation of e to the t xi. Okay, so here you use independence. Okay, and then you'll do what you do. Okay, so yeah, so these two steps, they're trivial here but they are important, and yeah, in generalizations these will be very tricky. Okay. Okay, so now let's see what happens in the expander, scalar expander case. So again, we have this sum f of vi, and you want to study what is the probability it's at least k epsilon. So you'll again do the same steps and reach. Okay, no, this is not the same. Okay, sorry. Yeah, so what do you do? So again, you reduce this to studying the moment generating function, expectation of e to the t sum over I f of vi. You have to study this, and now I'll do the following. This is sum over w1 to wk. Sorry, this is bad notation. So v1 to vk are random variables, and w1 to wk are instantiations of this random variable. Yeah, sorry. So this is 1 over n p of w1 w2. So initially you pick something randomly, then the probability of going from w1 to w2 p wk minus 1 wk and e to the t sum over I f of wi. Okay, so this is what it is. Just you write explicitly, and then yeah. So yeah, I mean there's an easy calculation to show that this can be written as the inner product between u Okay, I guess it's important I do this trivial step. So yeah, here e to the sum is the product of the exponentials, so you can write this as sum over w1 wk, 1 over and go as outside, the t f w1 p w1 w2 e to the t f wk minus 1 p wk minus 1 wk e to the t f wk. Okay, so yeah, it's a trivial step, but it's important. It won't be true in the matrix case. Okay, and then you just have to sort of state it for 1 minute, and you will see that this can be written as inner product between some vector e p to the k and u, where u is the all ones vector normalized, p is the transition matrix, and e is this diagonal matrix where you sort of put this f's exponentiated on the diagonal. Okay. Yeah, sorry, I haven't said something deep, but yeah, it's important in this proof that you break this e to the sum into products over exponentials. Okay? And this is only true in the scalar case, won't be true in the matrix case. And then you do some matrix analysis, simple algebra, and reduce to this form, and then you have to analyze this thing. And eventually, sort of, there are various ways of proving that this is at most e to the t k square over 1 minus lambda, something like this. Okay. Yeah, so there's a proof by Healy, 2008, and previous things used some perturbation arguments. Yeah, so once you reduce to this case, then there are standard arguments to take you further. Okay.
Why k square?
Sorry,
K.
t square k.
Yeah, t square.
T square k. Yeah, you want in t square. Yeah. Okay. Yeah. Okay, so I'll leave it here. So this is what happens in the expander Chernoff bond. Okay. Yeah, I mean the non-trivial part starts here, but already in this trivial step there's something going on in the matrix case. Okay. Okay, now let me tell you what happens in the matrix Chernoff bound. And here we'll use this inequality called Golden-Thomson. Sorry, I don't remember the year, maybe 65. So trace of e to the a plus b is at most trace of e to the a times e to the b. Okay. So even though in the so this is for Hermitian matrices a and b. So even though e to the a plus b is not equal to e to the a times e to the b, there is at least some relation between them in form of this inequality. Okay. And then taking too much space. I need a bigger. Okay, so you have random matrices and you want to analyze this thing. This you want to analyze. So again you will do the sort of the exponentiation.
This is the independent case.
This is in the independent case. So you will again write this as introduce a parameter t, take exponentials, that the spectrum of t xi is at least e to the t k epsilon. Okay, this step is the same. And now so sort of, so spectral norm is sort of hard to argue about, so I'll replace the spectral norm by trace, okay, just because trace is nicer. And then by Markov, this is at most trace of e to the, okay. So in the matrix case, this is our moment generating function, expectation of trace of exponential of sum, okay. This is the moment generating function in this case. And now what do you do? So yeah, so you have this, and now you want to use the golden Thomson, but you have many matrices, you wonder whether the golden Thomson is true for many matrices. Turns out it's not, okay. Yeah, I mean, so it's very easy to see, like even for 3 matrices this is not true. This is not trace of e to the b, e to the a, e to the b, e to the c, okay. So reason is that the left hand side is always positive, okay, but sometimes the right hand side can be negative, okay, and it's because products of PSD matrices are not always PSD, okay? So the traces can be arbitrary. So it's not true for 3 matrices. So what do you do? And it turns out in the independent case there's a nice argument that sort of applies this inductively, okay. So can apply just the 2 matrix golden Thomson inductively, right? I mean, yeah, you divide this into sum over n minus 1 matrices, and the nth matrix, apply golden Thomson, do stuff, get it out by independence, and sort of proceed, okay. But yeah, in a dependent case there doesn't seem to be any way to sort of way around this by just using the 2 matrix golden Thomson, okay. Yeah, so I won't get into the details why 2 matrix is enough in the independent case, but yeah, just doesn't seem to be enough in the dependent case, okay. So what do we do? Yeah, so then came this quantum people who proved the right inequality for us.
This is expansion.
Yeah, I won't do this, like, yeah, basically, yeah, this quantum people came and proved the right equality, and then when you combine it with Healy it works. So I won't go into the details, it's not illuminating, okay. But I want to tell you what this inequality is. Yeah, so in some sense our contribution wasn't much. There was this right inequality which you plug into Healy's framework and it works, okay. Okay, so what is the multi-matrix extension of golden Thomson? So we saw there that golden Thomson isn't true even for 3 matrices, and I said that it's not true because the right hand side could be negative, okay. So what if you made the right hand side positive, okay. So what if you try to do something like this, trace of e to the b, a plus b plus c is at most trace of e to the a, e to the b, e to the c. Now you divide by 2's in the exponents, and then take the matrix conjugation. Okay. So what if you do this? Now our previous objection doesn't apply. This is still, this cannot be negative. So is this inequality true? Turns out this is still not true. I can't tell you why it is not true, but they're just examples by computer simulation. So this is not true, okay. So what else can you do? So I'm going to write something crazy now, okay. So what if you do this? What if you introduce complex numbers in the exponent, just for the sake of it? So what if you tried this? So I'll denote MB by this matrix, e to the 1 plus IB A over 2, e to the 1 IB B over 2 e to the 1 I little b c over 2. So MB is this matrix, and what if you ask whether trace of e to the a plus b plus c is at most trace of MB conjugate transpose? Is this true?
For any b, for which b?
Let's say you fix some b, fix b is some real, and you'll say, of course not, what is this nonsense, right? Like, yeah, how can this be true? And it turns out it's not true. For any fixed value of b, this is not true, okay? But it turns out if you average over b's on the right hand side, it will be true. Okay? Yeah, so what is true is that trace of e to the a plus b plus c is at most you average over this expression, and you according to some distribution over b, over the real line. Okay? And this is true. This is an inequality due to Sutter, Bertha and Tomamiel in 16. Okay. Yeah, so this is true. You average over this crazy expression over
So what is this distribution? Does it have a nice description?
It's some kind of an exponential distribution. Yeah, I mean there's an explicit thing, but for our proofs it doesn't really matter what this distribution is. But yeah, there's an explicit.
And there is an extension for any number of matrices.
Yeah, so this extends to K matrices, any number of matrices, in the natural way.
The distribution on B doesn't change when you go to multiple matrices.
It doesn't change. Yeah. So this is what they proved, and when we plugged into Healy's framework and with a bit of trick, yeah, it wasn't optimal. We lost some log factors. And the reason is that these things in the exponent can be unbounded. Okay, so the distribution is over the whole real line, and they can be unbounded. And in the proof, sort of this leads to some loss. Okay, so we had some log epsilon factors loss, and then Yintad and Zhao, they proved the right inequality adapted to our setting. Okay, so I'll mention that now. Yeah, I should say that they proved this inequality in the context of quantum information theory. So even before, the Golden-Thomson inequality is related to this theorem called Leib's concavity theorem, which turns out to be equivalent to the monotonicity of quantum relative entropy. Okay? And this inequality they used to sort of prove some quantitative versions of the monotonicity of quantum relative entropy. Okay. So yeah, so inequality that we prove, so I'll denote MB tilde by this matrix where you have e to the EIB, so it's e to the IB in the exponent, a over 2, e to the IB, b over 2, e to the IB, c over 2. Okay. So this is this matrix MB tilde, and yeah, so what is true is that trace of E plus B plus C is at most and now you get some different distribution. And yeah, you might have to raise this to some power. It's not really important. So yeah, this is also true. But now the point is that in this matrices, the exponents are bounded complex numbers, and this really helps us get the optimal bounds. Okay. So yes.
Are those supposed to be all the same those three factors?
B,
Just
B
replace the e to the ib in the third one.
Another E.
sorry. Yes, sorry, thank you. Okay. Yeah, I mean, it's just something that looks similar to this. So yeah, so I want to tell you where these things come up, and yeah, it's not a surprise that since complex number is showing up, complex analysis will play a role. And yeah, so I'm quite illiterate in complex analysis. If I say something wrong, please correct me. Yeah, so what's going on? So yeah, so we are studying things of that form, right? So I'll denote, we have this map where g of z is equal to e to the z a over 2, e to the z b over 2. Okay, no, sorry, before that. Yeah, so how do we prove this inequality? So yeah, somewhere down the line we need some way of writing exponentials of sum as products of exponentials, okay? And such a representation is given by the Lee-Trotter formula. Okay, so this says that trace of e to the just e to the a plus b plus c, even though this is not e to the a times e to the b times e to the c, this is true at a very small scale, okay? So this is equal to limit theta tending to 0, e to the theta a, e to the theta b, e to the theta c to the power 1 over theta, okay? So sort of multiply a's by very small numbers, then you can write the exponential of sum as a product. Okay. And now
It's true for any number, and that's
right.
also for 2. That's what's used in the proof of Gordon-Thomson.
Right. Well, maybe the other proofs, but maybe this. Yeah. Okay. Yeah. So this is true, and now you have this product, and now you want some way of handling this. Okay. And so you will believe me that after some manipulations, not here, but let's say you look at log of the trace of e to the a plus b plus c, which is what you want to analyze, and using the Lee-Trotter formula and some simple manipulations, and write is as limit theta going to 0, 2 over theta log of the 2 over theta Schatten norm of this matrix. Okay, so I'll explain what this means. So G is this map e to the z a over 2, e to the z b over 2, e to the z c over 2. Right? These are the kind of things that are appearing there. And the Schatten norm of a matrix, let's say R Schatten norm, is just the trace. I mean, basically the rth norm of the singular values. Okay, so a r over 2 and 1. So yeah, after some manipulations using this formula, you can reduce it to analyzing the Schatten norm, some particular Schatten norm of this map G evaluated at theta. Okay. Now this is what you have to understand. Okay, so how do you understand that? So now, yeah, you have this map, which you can think of it as mapping a complex number to some n by n matrix, and you want to understand it around 0. Okay. So this is the picture. So you have 0, you have 1, you have minus 1, and here is a theta. Okay, and you want to analyze what happens on this map here. Okay. So what do we know about this map G, on this sort of half disk? Do we know its value somewhere over here? At 0, right? At 0 we know, but also on this imaginary line, we know that Z will be a unitary matrix. So any norm will be 1, any Schatten norm will be 1. So that's something we know. And then sort of you have this sort of I don't know what you call it, Poisson's formula or something, that allows you to write the value here as an average of the values on the boundary. and that's really what plays a part. Okay. So I'll just tell you what is the final ingredient and then stop. Yeah, so what goes into the proof is this. Let's say f is some analytic function on the half disk, okay, and we know that f of imaginary is at most 1 for all y. Okay, so here the value is at most 1. Then log of the value of the function at theta, okay, so the value here is at most for some constant times theta plus low order terms. So what we're really interested in is in the what goes next to theta, and it's this average log according to some distribution. Okay. So value here you can write as an average of values here, okay, according to some distribution, and this is what really goes into the proof of that. Basically, you have this map g theta. You'll define an appropriate f and use it to bound this Schatten norm.
And how do you get a handle on the values on this out?
Well, that's appearing in the inequality, right?
Oh, right, okay.
Right. That's what appears in the inequality,
Yeah.
and then you bound in your proof. Okay. Yeah. So I don't really have particular open questions in this area, rather than just sort of find applications of this expander matrix Chernoff bound. Yeah, I'll stop there. Thank you.